In part 1 of this series, we'll learn how to create point geometry by writing code in Vex. As a practical example, we'll be modeling a natural growth pattern called Phyllotaxis. And we'll also learn how to attach custom attributes to our points in order to make our pattern generator more powerful. So let's get started by dropping down a geometry node, hit return to dive inside, hit the tab key, and start typing Wrangle to see our options. To make geometry from scratch, we'll often be using a Detail Wrangle, but we also have nodes for wrangling point, primitive, and vertex attributes. And those correspond directly to the 4 types of attributes that we see listed in our geometry spreadsheet. And now if we drop down a point wrangle and a primitive wrangle side by side, we can compare them. And you'll notice that they're really just the same node under the hood. They're both an attribute wrangle, and the only difference between the two nodes is that the run over parameter has been preset to the different types of geometry. So our point wrangle runs over points, and our primitive wrangle runs over primitives. And we can, of course, change that to any type of geometry, and whatever code we now enter in this expression, our node is automatically going to run that code over each individual point or primitive or vertex in parallel. More typically, we might have some existing geometry wired into one of these inputs, which we would then modify using our wrangle. But in this case, we are making geometry from scratch, so we're going to get rid of these, and we'll drop down to Detail Wrangle, because eventually we are going to be writing our own loop inside our code, so we don't want the node implicitly looping for us. And the run over menu is giving us a little clue here that this code is only going to run one time instead of looping over geometry. And now we'll give our node a name and start entering our first code, which is a built-in function called addpoint. Now there are hundreds of built-in functions, so Houdini helpfully gives us a list that we can select from if you don't exactly remember what your function is called. And as soon as we type an opening parenthesis, it brings up a nice summary of how we can use this particular function. And the way we use a function is by passing it some information called parameters. It takes those parameters, does something, and gives us a result. So there are 2 ways we can do that with this particular function. We can either pass it a geohandle and a point number, or we can give it a geohandle and a vector position. And these 2 ways of calling the function are called signatures, and we're going to use the second one. And by the way, if you hover over a function name in the text editor and you hit the F1 key, it brings up the documentation for that command, which gives you a lot more complete information than what you see in the pop-up summary text. So the first parameter then to our addPoint function is the geohandle, which is just a number which corresponds to the 4 inputs on our wrangle node, numbered 0, 1, 2, and 3, where 0 is the main input. And it's so common that we use 0 that you'll quickly get in the habit of automatically typing it before any other parameters to these Vex functions. And for our second parameter, we'll enter a vector literal, which is 3 numbers enclosed in curly braces representing the x, y, and z coordinates of our point position. And we'll follow that with a semicolon, which concludes one complete statement of code. And we'll talk more about statements as we continue, but for now, just get used to including that semicolon after each line of code. Okay, so far nothing's happened, but if we're ready to commit this change, we can now click anywhere outside our text editor, or you can hit the escape key, which is the way I prefer to do it. And now we'll see we have this tiny white dot at the origin representing our new point, and we can make that a little bit more visible by turning on display points in our viewer. And we can also see that we now have a single point listed in the geometry spreadsheet. And also if we middle mouse on our node, we'll see we have a single point listed there as well. So far so good. So now let's change our x coordinate to move our point over. And we see that now our point is at 1, 0. And let's try also 0.5, 0.5. We'll hit escape. And now we see that our point has moved 0.5 along the x-axis and 0.5 along the y-axis. And for the rest of this tutorial, we're just going to be leaving the z-axis at 0. Okay, so let's make our first variable now, which is a way of assigning a name to a piece of data that has a particular type. So here we have this vector of 3 floats, which is the position of our point. So let's make a new variable of type vector named POS. And now we can cut this value and replace it with a reference to our new variable. And then we can go ahead and assign that value to our variable using the equal sign. So the first line of code is our declaration, and the second line is our assignment. And we'll very often do both steps in a single line of code where we declare a variable and then immediately assign an initial value to it. Now let's try using this new variable inside our vector and see what happens. And if we hit escape, we will see that we now have an error message. And if we middle click on our wrangle node, the message is unexpected identifier at line 4 of our code. So a variable name is a type of identifier, and this is telling us that Vex syntax doesn't actually allow a variable inside of a literal. It's expecting to see only literal float values here. So instead, we're going to use another built-in function called set, which allows us to construct a vector using separate expressions for our three x, y, and z components. And if we now delete our literal expression and hit escape, we'll see that we're now back in business and that our point has moved over to 0.2 on the x-axis. We can only declare a variable once, but we can assign to it as many times as we want. So if we write a new value, it overwrites the previous value, and we can see that our point has moved to a new position. Okay, we're ready to make our loop. So let's reset our point position to the origin and delete the x variable that we no longer need. And let's declare a new integer type variable I for index and another one called numPoints. And because these are of the same type, we can declare them together on the same line separated by a comma. And we'll initialize numPoints to 10, and now we'll build a loop that's going to create 10 points for us. So a for loop is just the word for followed by parentheses followed by curly brackets, and everything that's inside the curly brackets gets grouped together into what's called a compound statement or a block. And that's the code that's going to run over and over again each time our loop executes. And then inside our parentheses, we have three expressions that are separated by semicolons. The first one is the initializer, so we're starting off with I equal to 0 before we run our loop. And then each time through, we compare I to numPoints, and as long as this comparison expression is true, our loop runs. And as soon as it's false, our loop stops. And then lastly, we have an expression that runs after each iteration, where here we're just incrementing the value of I by 1. And it's important to know that the comparison happens before each iteration. So it is possible for the loop to not execute at all if our comparison expression is already false. Now when we hit escape to commit the change to our code, we see that we now have 10 points in our geometry spreadsheet, numbered from 0 to 9, but they're all sitting at the origin, so they're being drawn on top of each other. So let's go ahead and change our code now so that we're doing something different each time through the loop. We'll make a new float variable called step, and we'll give that the value 0.1. And then we will change our x component to be I times step. So each time through the loop, our x component changes. We hit escape, and sure enough, now we see them increasing by 0.1 each time through our loop, and we see our 10 points spread out along the x-axis. If you have some experience in other programming languages, you might have noticed that we're multiplying an integer with a float here, which can't directly be done, but it works because Vex is automatically promoting that integer for us behind the scenes. But if you want to be more explicit about it, you can cast the variable yourself using this syntax with float inside parentheses. Okay, notice that we don't have a point at 1, 0. And this is happening because as soon as I reaches 10, this comparison becomes false and our loop exits before it executes. So how could we change this if we wanted to? One idea would be to ask for 11 points, and that would allow the index I to make it all the way to 10. Another idea would be we could keep it at 10 points, but change our comparison to be less than or equal to, and that would allow one more iteration on the loop, which is maybe not as good because now we're getting 11 points when we asked for 10. So we could change to start at 1, and now we're back to getting 10 points, but we've lost the origin. So it just depends on what your goals are. And this is just something to be aware of when you're using a for loop, but the most common idiom is to start from 0 and use a less than comparison, and that way you know how many iterations you're getting. Now let's clean up our code a little bit, starting with this incrementer expression. So here we're reading from I, we're adding 1 to it, and then we're reassigning that back into I. And this is such a common thing to do that there's a more concise expression for that, which is plus equals. And the fact that we're adding 1 is also super common, so we can make that even shorter. So I++ just means increment the value of I by 1. We're not using I anywhere outside of our loop, so we might as well declare it right here. And that means we can remove it from up top. And that actually means we can remove numPoints as well and go ahead and just declare that at the same place that we're initializing it. Likewise, for our vector position, we're not using that anywhere outside of our loop, so let's remove this declaration and move it inside. And lastly, we can remove this cast on our integer since it isn't strictly necessary. And now we have some nice, clean, concise code. Before we move on, let's consider another way we could have done this. We could make a float x variable and initialize it to 0. And then each time through the loop, we could simply set our x component to x and then increment it by our step value at the end of each iteration. And when we commit our change, we see everything looks the same. But this approach is not as recommended because floating point arithmetic is inherently imprecise, and each time you do an operation, you get a rounding error. And so when we accumulate our value over our loop, we also accumulate the rounding error, which doesn't matter for a case like this, but if we had thousands or millions of iterations, then we could run into problems where our accumulated value starts to drift. So let's undo that change and use our original approach where we multiply an index, which is generally a better practice. And now we're going to add some parameters to our wrangle to make it more interactive. So let's replace these hard-coded values with the ch built-in function, which stands for channel, and this refers to a float parameter on this node or some other node. Likewise, chi refers to an integer channel. And by convention, we use underscores instead of spaces on these parameter names. Now, when we commit our change, we see our points have gone away, and that's because we haven't yet defined these channels. And now clicking on this Create Spare Parameters button will look through our code, and it will automatically make spare parameters that match the names of our channel expressions. And you can see that the reason we lost our points is because we've defaulted to 0 points, and if we restore our values, we're back to where we started. These automatically generated parameters are just like any others that we could make ourselves. So let's go into the parameter interface and go ahead and just tweak our number of points so that the range slider goes to 100. And now we can use our sliders to update our parameters interactively instead of having to change our code. Okay, great. So now to arrange these points into our actual Phyllotaxis pattern, we're going to use polar coordinates, meaning that we're going to define our point position as a distance from the origin and an angle of rotation away from the x-axis, which we're going to call r and theta. And if we imagine our point sitting at the corner of a right triangle, we can easily convert our r and theta back to x and y by taking the cosine and the sine of our angle times the radius. Cosine and sine are both built-in math functions, so let's go ahead and put that in our code. Our x component will be r times cosine theta, and our y will be r times sine theta. And if we hit escape, we get an error message, middle mouse, we see that we have undefined variables r and theta. That makes sense because we have to declare our variables before we can use them. So let's go ahead and do that. Let's give r a value of 1, so our point will be sitting 1 unit away from the origin. And let's make theta 0, so it'll be sitting right on the x-axis. We hit escape and we see our point sitting at 1, 0. And now if we plug in an angle of 90, we would expect that to be sitting on the y-axis, but in fact it does not. And the reason is because cosine and sine are both expecting their angles to be expressed in terms of radians instead of degrees. So we can either convert our value using the built-in radians function, or we can just express our value in radians in the first place. So let's make a variable tau, which will equal 2 times pi. And notice that we haven't declared pi, but there's no error message. And the reason is that pi is a predefined built-in variable that Vex provides for us because we need to use it so often. And let's make another variable called step angle. And we'll just take our full circle tau and divide that by 16. So our step angle is 2 pi over 16. Now if we plug that in here and multiply by I, now we see that we're moving a 16th of a full circle with each iteration. And likewise for the radius, let's use this step value we already have and multiply that by I. And now we see that our radius is increasing with each iteration as well. So now it's just a matter of finding the right expressions for r and theta to make our Phyllotaxis pattern. And let's start with our angle theta. When we have two numbers where the ratio of the smaller one to the larger one is the same as the ratio of the larger one to the sum of the two, that's called the golden ratio. And just like pi, that's an irrational number, but with a little bit of algebra, we can express it in terms of the square root of 5. And you can check out the Wikipedia page about the golden ratio if you want to find out more about why this is true. And now if we make a rectangle whose sides are in the same proportion, that's called a golden rectangle. And the cool thing about a golden rectangle is that if you subtract a square, you get another golden rectangle. And in the same way, if you add a square to the longer side of a golden rectangle, you get another one. And if you connect the corners of this arrangement of squares in a certain way, you get a golden spiral. And finally, if we take a circle and divide it into two angles that have this same proportion, we call that the golden angle. And once again, with a little algebra, we can express the golden angle in terms of the golden ratio. And now if we use that angle to space out our leaves, we discover that each individual leaf never lands at exactly the same angle as any other. And taken together, our leaves start to form a spiral pattern that looks very much like the Phyllotaxis patterns that we see in natural plants. Let's go ahead and define our golden ratio, phi, in terms of the square root of 5 by translating the equation that we saw earlier into code. But the way I have this coded up so far isn't quite going to work because the division actually will happen before the addition. And the way we can fix that is by using parentheses to force our addition to happen first, and then that whole quantity will then get divided by 2, which matches our formula. And then we can now define our golden angle as 2 pi over phi squared. And when we commit our change, we see our spiral pattern starting to emerge. But let's double check our math by saving this step angle into a new geometric attribute with the same name. So this f at step angle syntax means let's make a new float attribute called step angle. And because we are in a detail wrangle, we've just made a detail attribute, which we can now see in the geometry spreadsheet. And that value is in radians, so let's go ahead and convert it to degrees using another built-in function. And now we've confirmed that we have the value that we expect. And I'll be talking a lot more about detail attributes in a future episode of this series, but for now, just think of it as a way to inspect a value in our code, much like you would use a print statement in other programming languages. Okay, so now let's work on the radius. And let's start by taking our index value and dividing it by our number of points so that our last point is always 1 unit away from the origin. And now if we commit our change and inspect our point values, we see that something has gone wrong. Everything is now sitting at the origin. So what happened? Our problem here is that I and num points are both integers, so Vex did an integer division which just gave us a 0 as a result. And to solve that problem, we can just cast one of our two variables to a float, and that gives us the floating point division that we need. So unlike our earlier example where the typecast was optional, in this case we actually need it in order to get a correct result. Let's check our radius values by dropping down a circle, set the type to be primitive, and turn on the template flag. And now we can see visually that our outermost point is not quite touching the circle. And the reason for that is because our loop stops while I is still 1 less than num points. Let's try fixing that by subtracting 1 from num points so that this division will now have the value of 1 at our last iteration, and sure enough, our outermost point now has a radius of exactly 1. But in this case, we might actually prefer to lose the point that's sitting at the origin. So let's undo that change, and instead we'll add 1 to I. And so now at our last iteration, again, we have a radius of 1, but at our first iteration, we no longer have a radius of 0. Okay, great. Looking good so far, but I don't love the spacing of the innermost points around the origin. So let's consider shaping our radius values in some way other than taking uniform steps with each iteration. So let's delete the step size parameter that we're no longer using and add a new float parameter using chf called exponent. And again, chf is a synonym for ch. And while we're at it, let's also add a radius attribute so that we can control the scale of our whole pattern. And now we can hit this button again to see our new parameters, but we still have this unused slider hanging around. So let's go to Edit Parameter Interface where we can select that parameter and hit the delete key to remove it. And while we're here, let's also set more convenient slider ranges. We'll set our number of points to go from 0 to 1,000, and we'll set a range of 0 to 2 for both our exponent and our radius. And we can also set default values for our parameters by switching to the Channels tab. So let's set a default of 1 for our exponent and a default of 1 for our radius. And now we can take advantage of our new exponent parameter using another built-in math function called pow, which raises the first argument to the power of the second argument. Let's plug in our radius as the first argument and our new exponent as the second argument, and now we can see the visual effect of raising the radius to a power less than 1 and greater than 1. And now let's crank up our point count, and if we experiment with our slider, we discover that an exponent value of exactly 0.5 gives us the most even distribution of points. And raising a number to 0.5 is the same as taking its square root. And we'll talk a little bit later about why that particular value is special. But while we're here, let's not forget to also multiply by our new radius parameter. Okay, now that we're seeing these really interesting spiral patterns, let's talk about why they might be emerging when all we're really doing is stepping around repeatedly by this one special golden angle. And that brings us to the famous Fibonacci sequence, where we start with a 0 and a 1, and where each subsequent Fibonacci number is the sum of the previous two. As it turns out, there's a beautiful connection between this sequence and the golden ratio, because if you take any Fibonacci number and divide it by the one before it, You get a ratio that rapidly converges on the golden ratio as you continue up through the series. So with that amazing connection in mind, things get interesting when we start to look at connecting the points in our pattern. Starting from the lowest numbered points, if we connect together every 13th point in our loop, we get a spiral pattern with 13 curves. The same thing happens with any Fibonacci number that we might choose, but if we stick to these lower numbers and combine them together, we start to get some really cool patterns. But notice that this doesn't happen if we skip by any number in general. It's only the Fibonacci numbers that have this special behavior. Okay, now that we've defined the positions of our points, let's learn about how to add additional attributes to them. Let's start by cutting our point count in half to 500, deleting the circle that we no longer need, and let's drop down a platonic solid node, set the solid type to be Utah teapot, and set the radius to be 0.05. And I'll hit the H key to frame that in our view and turn off point display as well. And the reason I'm choosing this geometry is because the spout points along the positive x-axis, the lid points along positive y, and the starboard side of our vessel points along positive z, which makes it perfect for instancing onto a point because we can see its orientation. And to keep things moving quickly, let's drop down a packed node after our geometry and drop down a copy to points, and we'll wire our packed primitive into the left input and our points into the right input. And now we have 500 teapots that are all unfortunately pointing in the same direction. But it's a great example of why we might create custom attributes that a downstream node can take advantage of. In this case, we can transform using target point orientations, which is a feature that's turned on by default in the copy to points node. Let's take a look at the documentation for this node. And if we scroll down, we'll see a link to instancing point attributes. And click on that, and this will show us all the attributes that this node expects to see and can take advantage of for transforming its copies. And my favorite way of setting orientations is by using this orient attribute, which expects a rotation around an axis to be encoded into a vector of 4 numbers called a quaternion. And in order to make a quaternion, we need to do a little bit of math, which I'm not going to explain carefully here because the point of this example is to learn how to add attributes, but I will explain this in more depth in a future video. We'll start by making a vector that points from the origin to our point position, and we will make its length equal to 1 using the built-in normalize function. For our second vector, we'll take the first one and rotate it 90 degrees around the z-axis so that it's now perpendicular to the first vector. And lastly, we need a third vector that's perpendicular to the first two. And normally we could calculate that using the built-in cross-product function, but in this case, we know that we're always going to be pointing along positive z, so we might as well just hard code that value using a literal. Next, we'll combine our 3 vectors into the rows of a 3 by 3 matrix using the very same set command that we used earlier to combine 3 floats into a vector. And here, putting these 3 arguments in different orders will give you different orientations, so I encourage you to experiment with that and see what you get. Our last step is to convert our orientation matrix into a quaternion using another built-in function. And now, finally, we have the quaternion value that the copy to points node is expecting. Next, we need to grab the point number that's returned by the addpoint function and put that in a variable. And now we can plug that into the setPointAttrib function. And we need to pass that the usual geohandle argument, the name of the attribute, the point number that we're setting, the value that we just calculated, and an optional last argument, which you can read more about in the documentation. And the name of the attribute has to exactly match what the copy to points node is expecting. And we give it our new point number and the value that we just calculated. And we can skip the last argument. And if we hit escape, we now see much nicer looking orientations on our copies. Okay, great. Now, are there any other attributes that we might want to consider adding that would be potentially useful downstream? Well, we've already calculated r and theta, our distance and angle for each point, so we might as well just pass those along. So let's go ahead and add 2 more setPointAttrib statements, and we'll just name our attributes after our variables. And once we commit our change, we see our new attributes showing up in the geometry spreadsheet and updating as we expect. And let's just wire up a quick example of how that might be used. We'll make a platonic solid, type cube, set a small radius again, and replace our teapot with that. Then we'll drop down a color node and set to ramp from attribute using the R attribute and set a ramp. Okay, cool. So let's take a quick look at another way we could have done this just so we can talk about the @ shorthand for adding attributes. Let's start by selecting our Wrangle node and enclosing it in a subnet. Now we can give that a nice name, and convert our subnet into a digital asset by right-clicking, create digital asset. We can accept all of the default settings, hit create, and now we have a new node that contains our pattern generator. And to add parameters, we'll switch to the From Nodes tab and navigate down inside our HDA to the generated channel parameters, which are the same channels that we created by hitting the button on the Wrangle node. Hit accept, and now we see the same controls on our HDA. Now when we dive inside our digital asset and take a look at our Wrangle, we can see that by doing it this way, the input channels on our Wrangle have automatically been expressioned up to the matching parameters on the asset itself. And this is the recommended way to set up a Wrangle. We always want the channel expressions in our code to refer to spare parameters on the Wrangle itself, and then those in turn are connected to other controls through expressions. Now that we've wrapped up our pattern generator inside of an asset, let's try implementing it a different way. Instead of creating our points using code, we're going to create them using built-in nodes. So we'll drop down a default grid and wire that into a default scatter. And now we can see that our points are laid out along the XZ axis, but we don't really care because we're about to overwrite their positions with new values using a Wrangle. Now let's select our Wrangle, and on the number of points parameter, let's copy that parameter. And we're going to paste the expression from that parameter into the force total count parameter of our scatter node. And now our point count is coming from the same parameter on the asset. And now we can option drag our Wrangle to make a copy, and we'll wire the output of the scatter into the first input, give it a name, and we're going to change the runover type from detail to points. And so now we no longer need the loop in our code because the Point Wrangle is implicitly looping for us. So let's remove that, and we're going to unindent everything that was inside our block just to make it a little cleaner, and then replace any references to our index variable I with @ptnum, which is a built-in attribute provided by Vex that gives us the point that we're currently operating on. And now we can remove our addPoint call because instead of creating a new point, we're just going to assign a new position value to an existing point, which we do with this v@p shorthand. Similar to what we saw before, we're assigning our position value to a vector attribute p. And down here, we can do the same thing with our other attributes, where p is the shorthand for a vector 4, and f is the shorthand for a float. And because we're now in a Point Wrangle, we can use this more concise syntax to create point attributes, instead of using the setPointAttrib call that we needed to use inside a Detail Wrangle. Okay, now let's commit our change, make sure everything looks the same as before, and now we can connect our new Wrangle to the output of our asset. And so nothing's changed for the user, even though we've changed our implementation underneath. And the takeaway from this example is just to show when you can use that attribute shorthand and when you can't. But in this case, I think our first approach is cleaner because it's more self-contained and it doesn't have any wasted computation. So let's plug that in again, and now we have a nice polished tool that works well with other native Houdini nodes. If you have experience programming in other languages that are similar to C, then hopefully everything that we've covered will feel pretty familiar. But in case you're new to programming, here is a summary of the terminology covering all the things that we discussed, and here's a list of the various Vex functions that we covered so far, which is actually quite a bit. And to learn more, I highly recommend that you check out the documentation for the Attribute Wrangle node, which you can find in 3 different ways. With the node selected, you can click on this question mark icon at the corner of the parameter pane, or you can right-click on the node itself and choose Help, or you can find that very same Help option in the menu at the top left corner of the parameter pane. And those all bring you to the same place, the documentation for the Attribute Wrangle. There you can find a link to the Vex language, and if you scroll down, you'll see another link to the Vex language reference. And there you can find all the details you'll ever need to know about how to code in Vex. In part 2 of this series, we'll learn how to connect points together to make curves and polygons, so please remember to subscribe if you'd like to be notified about that or other future tutorials. And finally, let's wrap up by returning to the question of why taking the square root of our radius turned out to be just right for getting an even distribution of points. To investigate that, let's go to a new scene, drop down a geometry node, dive inside, create a Detail Wrangle. And let's go ahead and create an integer channel for our number of points as we did before, and hit our Make Spare Parameter button, and let's set our point count to 10,000. And now we'll use a for loop again to create a bunch of new points, but this time we're going to assign random numbers to our x and y positions. The built-in rand function takes a seed parameter and returns a number uniformly distributed between 0 and 1. So we need to pass a different seed in order to get a different random number, and notice that we're including I in our seed so that we get a different random point each time through the loop. And as before, we'll construct a vector and we'll pass that to the addPoint call to make a new point. And when we hit escape, we see that we get a nice uniform distribution of points in the unit square. And now to do the same idea on a unit disk, let's try using polar coordinates. So we'll change x to r, and we'll change y to theta, and multiply that second random number by 2 times pi to make it an angle in radians. And then as before, we can convert our polar coordinates, radius, and angle back into Euclidean x and y positions by using r cosine theta and r sine theta. And once again, we see a similar issue where our points are more densely concentrated around the origin. So let's try taking the square root of our radius again, and we see that that solves the problem. And to get some intuition for why that's the case, let's imagine dividing our disk into strips with equal steps along the radius. It's easy to see that these uniformly wide rings have very different areas, and yet our random radius is equally likely to land in any of them. But if we take the square root of our steps along the radius, then we end up with strips of uniform area rather than thickness. And finally, if we imagine having an infinite number of strips that are all infinitely thin, then it might start to feel intuitive as to why taking the square root of an individual point's radius moves it to the right place. And as it turns out, Vex provides a whole family of built-in functions for doing correct uniform sampling over different domains. So let's rework our code one more time, combining our 2 random numbers into a vector 2, which we'll call uv, and we can get rid of our 2 pi factor. And we pass that to a built-in function sample circle uniform, which returns another vector 2, which is our uniformly sampled point on a disk. And now if we plug that back into the x and y of our point position, we get a result that's very similar to what we get when we do the math ourselves. And now let's hover over our function call and hit F1 to bring up the documentation for this command. And sure enough, it's using the exact same math that we were just using. Thanks so much for listening. I hope you enjoyed this and found it useful. And please stay tuned for part 2 about connecting points into polylines. And I hope to see you again in a future video.